The cosmos hums with secrets we are only beginning to hear. These are the whispers of gravitational waves, ripples in the fabric of spacetime itself. By the end of this exploration, you will know the 27 most baffling signals ever detected, cosmic tremors that defy our current understanding of physics. What happens when a collision in the void produces no light at all? And why would a gravitational wave appear to beat the speed of light itself? How many of these cosmic mysteries do you think will remain unsolved in our lifetime? Think of the gentle ripples from a stone dropped in a pond, a perfect echo of how the universe itself distorts. Gravitational waves are those same ripples, but moving through the very fabric of spacetime, created when immense objects like black holes accelerate and collide. Albert Einstein predicted their existence over 100 years ago, yet it took until 2015 for humanity to finally capture one. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made that first historic detection, giving us an entirely new sense with which to perceive the cosmos. Nobel laureate Kip Thorne called this the music of the cosmos, a way to hear the universe. We can now listen to the violent mergers of black holes, events that emit no light whatsoever, revealing a dark universe previously hidden from our telescopes. These waves race across the cosmos at the speed of light, carrying encoded information about their violent births, the specific masses of the colliding objects, their spins, the very nature of the cataclysm, all are imprinted in the signal. But these ripples fade as they travel, becoming incredibly faint by the time they wash over Earth, making their detection one of the most remarkable feats of human engineering. The key to reading this cosmic music lies in two main characteristics. The amplitude tells you the wave's strength, a whisper from a small event or a shout from a colossal collision. The frequency reveals the type of event unfolding. A black hole merger, for example, produces a classic chirp, a signal that starts with a low frequency and rapidly rises to a crescendo before cutting off abruptly. It is a sonic fingerprint of a catastrophic dance. This foundational understanding makes the detections that follow not just confirmations, but profound mysteries. Why would some of these cosmic events produce a silent ripple with no flash of light to accompany it? What could cause a signal that appears to break the universal speed limit? The established rules set the stage for the anomalies that truly make us wonder what else is out there. In 2017, the Cosmic Symphony produced a note that should not exist. Detectors picked up a gravitational wave signal with an unusually high frequency, a piercing chirp that did not match the predicted song of any known cosmic event. Dubbed GW170817 follow-up, this signal arrived alongside a powerful gamma-ray burst, an event typically attributed to the collision of two neutron stars. But this was no ordinary collision. Its features were all wrong. Think of hearing a familiar song on the radio, only to realize one instrument is playing in a key no one has ever heard before. This signal's rapid oscillations and incredibly short duration made it a profound puzzle. Could it simply be random noise, an illusion created by the instruments themselves? Or was it the first whisper of a new type of compact object, something stranger than a black hole or neutron star? Experts like Dr. Maya Fishbach have publicly speculated that it might point to interactions involving exotic matter, or even subtle effects related to the quantum nature of gravity. Detailed computer analyses only deepened the mystery. The signal refused to align with any simulation of a standard binary merger, where two dense objects spiral inward. This failure to fit any known model opened the door to truly wild possibilities. Perhaps we were hearing the faint echo of a primordial black hole, a relic from the universe's first moments, colliding with something unseen. Or maybe it was evidence of an object entirely novel to our physics, a cosmic entity we have not yet even named. This single, unidentified frequency reminds us that for every question our new sense of hearing answers, it asks two more. It is a stark and thrilling sign that the cosmos is far stranger than we ever imagined, and that the rules we have written are merely the first draft of a much grander story. But the universe holds deeper mysteries than single, fleeting notes. Beneath the loud crashes of black hole mergers lies a constant, subtle hum, a background noise that permeates the cosmos. This is the gravitational wave background, a collective whisper from countless unresolved cosmic events all happening at once. Imagine walking into a vast, crowded stadium, hearing the roar of the entire crowd as a single, indistinct sound. That is what scientists expected to hear, but instead of a uniform roar, they are detecting a strange, rhythmic pulse hidden within the noise, a pattern that defies all expectations. This anomaly, uncovered by precise timing of distant pulsars, suggests the hum is not just from the expected chorus of supermassive black hole binaries. These cosmic lighthouses, spinning with impeccable regularity, are being ever so slightly jostled by the passage of gravitational waves, and the pattern of their timing shifts is telling a new story. Researchers like Dr. Chiara Mingarelli point out that this unexpected structure could be the signature of phenomena from the universe's violent infancy. We might be hearing the faint echoes of cosmic strings, hypothetical defects in spacetime left over from the Big Bang, vibrating like colossal violin strings. Or perhaps it is the remnant of a phase transition, when the newborn universe suddenly changed its fundamental state, sending shockwaves through the fabric of reality. The data reveals another baffling clue, an irregular clustering of this background signal. Some regions of space seem to hum louder than others, a finding that challenges the very notion of a uniform cosmic background. Could this be evidence of dark matter interacting in ways we never predicted, or even a vibration leaking into our universe from hidden dimensions? This persistent, structured hum forces us to ask a profound question. Are we finally listening to the echoes of creation itself, a direct recording of the universe's first turbulent moments? If this background is a window into that primordial era, then our entire timeline of cosmic evolution may need to be rewritten. And if the background hum holds such profound secrets, then the individual events that scream above it must be even more extraordinary. Sometimes the loudest message from the cosmos is a profound and unsettling silence. In the summer of 2019, observatories recorded a gravitational wave event of staggering power, a collision so massive it should have set the universe ablaze. Yet when every telescope on Earth and in space swiveled to look, they saw nothing. No flash of light, no burst of X-rays, not even a faint radio whisper. This event, known as GW190521, was a silent explosion in the absolute dark. The signal itself was bizarre, generated by two black holes of impossible size. Each was far heavier than any star should ever produce, falling squarely into what astrophysicists call the pair instability mass gap. According to our best models of stellar evolution, stars in this mass range should not collapse into black holes at all. They should be utterly torn apart by their own death throes. Yet here they were, not only existing but merging. The lead scientist on the LIGO team, Dr. Vicky Calogera, and her colleagues were left with a difficult puzzle. One leading theory suggests this merger happened in a densely packed environment, like the chaotic core of a globular cluster, where so much gas and dust could have smothered any light before it escaped. An even more exotic possibility is that these were not stellar black holes, but primordial ones, forged from the raw energy of the Big Bang itself. These ancient relics would carry no surrounding starlight or accreting material, making their collisions inherently dark. This signal's other peculiar traits, like the strange precession of the black hole's spins, further distinguish it from a typical merger. This points to the truly radical idea that we might be witnessing a collision within a vast halo of dark matter, an environment that could fundamentally alter how such an event unfolds. The silence of GW 190521 is not an absence of evidence, it is evidence of an absence. It forces us to confront the possibility that we are detecting a part of the universe that is fundamentally dark, a sector of reality that does not interact with light at all. If these invisible giants are real, then our census of the cosmos is missing its most massive players. And if collisions can occur without a single photon, what other fundamental laws might these dark events be bending, or even breaking? The dance of cosmic giants is not always a meeting of equals. In 2020, a gravitational wave washed over our planet carrying the signature of a truly bizarre partnership. This event, GW 190412, recorded a black hole merger where one partner was over 3 times more massive than the other. Imagine the gravitational waltz of a sumo wrestler paired with a ballet dancer. This extreme asymmetry created a ripple in spacetime with a unique and complex fingerprint, a waveform rich with higher-order harmonics that scientists rarely get to observe. These subtle vibrations within the main signal acted like a cosmic strobe light, illuminating details of the black hole's spins and orbital paths with unprecedented clarity. Expert astrophysicist Dr. Salvatore Vitale and his team realized this was not a typical binary born from 2 stars that lived and died together. Such a lopsided pair is a cosmic oddity. The leading theory points to a violent and crowded origin. Picture a dense globular cluster, a stellar city where millions of stars are packed tightly together. In such a chaotic environment, black holes can sink to the center and engage in a gravitational game of pinball. A lone black hole might capture a much smaller partner, a pairing that would be highly unlikely in the calm suburbs of the galaxy. This is known as a hierarchical merger, where the heavier black hole could itself be the product of 2 previous black holes that merged, only to later find and consume a third, smaller one. The existence of GW 190412 suggests that these mismatched pairs might be far more common than our models predicted. It forces a profound question about the neighborhoods where black holes reside. Are we looking at the dynamic, chaotic cores of star clusters, where gravity writes its own rules for partnership? If so, then our cosmic maps are missing the most turbulent and active districts. This single asymmetric chirp hints at a universe where black holes are not just solitary ghosts, but social creatures in crowded stellar metropolises, constantly pairing and repairing in the dark. And if such strange couples are forming all around us, what other impossible-seeming mergers are we on the verge of hearing? The cosmos has a way of hiding its most dramatic events in plain, empty sight. In 2021, detectors recorded a gravitational wave from a source that should not have been there at all. This event, GW2-10210, originated from a cosmic void, a region of space so profoundly empty it contains almost no galaxies, no stars, and seemingly no possibility for the violent merger that created the signal. It was like hearing a single, powerful shout from the heart of a deserted, silent canyon. The localization of this ripple was precise, and it pointed unequivocally to one of the universe's emptiest neighborhoods. Astronomers, including Dr. Daniel Halls, were immediately confronted with a puzzle. How did the objects that created this wave, likely a pair of merging black holes, end up in such an isolated place? The signal itself suggested a relatively low mass event, the kind typically born from stellar systems. But stars are not born in voids, they are born in the crowded disks of galaxies. So how did their black hole remnants get there? One theory posits these are primordial black holes, ancient relics from the Big Bang that were scattered across the cosmos like random seeds, some of which landed in these desolate stretches. Another idea suggests they are rogue black holes, ejected at incredible speeds from their home galaxies during previous violent mergers, sent flying across the intergalactic dark until they found each other. There are more speculative possibilities, too. Could an invisible structure made of dark matter have provided the scaffolding for a black hole to form directly in the void, a collapse triggered by something other than a dying star? Or was the signal itself warped and magnified by an invisible clump of dark matter acting as a gravitational lens, creating a phantom echo that made a distant event appear to come from nowhere? This lone echo from the void does more than present a single anomaly. It challenges our fundamental map of the universe. We assume that where we see matter, events happen, and where we see emptiness, there is nothing. But this signal whispers that the empty spaces might be teeming with invisible activity, that our cosmic charts are missing entire continents of dark matter or populations of wandering black holes. If a collision can happen in the deepest void, then our understanding of where cosmic violence occurs is fundamentally incomplete. What other secrets are these silent stretches of space concealing from our telescopes, waiting only for our new sense of hearing to reveal them? There is a faint, rhythmic ticking hidden deep within the cosmic noise. As scientists sifted through the mountain of data from LIGO and Virgo, they began to notice something strange. Certain gravitational wave signals seemed to be repeating. It was not a steady, predictable beat like a metronome, but an irregular pulse, a cosmic clock that ticks at random, unpredictable intervals. This repeating pattern anomaly defies everything we know about the orbits of binary systems. When two black holes or neutron stars spiral together, they merge in a single, catastrophic event. They do not get back up and do it again. So what could possibly be causing these recurring ripples in spacetime? Experts like Dr. Neil Cornish have proposed that we might be seeing a population of sources locked in a resonant configuration, a complex gravitational dance where multiple objects interact, producing a wave each time they swing past a certain point. Another possibility involves a single, incredibly dynamic object, like a pulsar with wildly precessing jets. Imagine a spinning lighthouse whose beam does not just rotate, but wobbles erratically. If such a beam were made of immense energy and mass, its lurching motions could theoretically fling off gravitational waves in a sporadic pattern. The varying intervals between these events point to something even more exotic. Perhaps we are hearing the faint echoes of cosmic strings, hypothetical flaws in the universe's fabric that can snap and vibrate like a colossal, plucked guitar string, sending out sporadic shudders across the cosmos. These vibrations would be a direct test for physics beyond the standard model, offering a glimpse into the universe's most fundamental structure. So we are left to wonder, are we detecting the irregular heartbeat of a hidden cosmic engine, a machine operating on laws we have yet to comprehend? This subtle repetition forces us to rethink our entire search strategy. Instead of only listening for one-off crashes, we must now also listen for recurring whispers. If spacetime itself can echo with such patterns, what other cycles and rhythms are we missing? And if a repeating signal can so thoroughly challenge our models, What about a single event that involved an object we cannot even classify? The formation of a black hole should follow a set of cosmic rules, but sometimes the universe writes its own. The signal known as GW190521 did more than announce a collision. It created a monster, a final black hole weighing in at around 150 times the mass of our Sun. This placed it squarely in the desert of the intermediate mass range, a category of black hole that had been almost entirely theoretical. These are the missing links, the bridges between the stellar mass black holes forged from dying stars and the supermassive behemoths that lurk in galactic centers. According to our best models of stellar evolution, a star large enough to collapse directly into such an object would be torn apart by pair instability supernova, leaving nothing behind. So how did this 150 solar mass giant come to be? Researchers like Dr. K.E. Savick-Ford have proposed a dramatic origin story. This was likely not a first-generation merger, but a second-generation one. Imagine two black holes, each themselves the product of earlier mergers, meeting in a dense stellar cluster and combining into this unprecedented heavyweight. The signal itself was a brutal, brief burst, a high-frequency chirp that lasted less than a tenth of a second, indicating a rapid and violently direct collision. This supports the idea of a chaotic environment where such sequential mergers are possible. An even more exotic possibility is that we witnessed the union of two primordial black holes, ancient relics from the Big Bang that bypassed stellar death entirely. This single detection forces a profound question about the building blocks of the cosmos. If intermediate mass black holes are forming through these hierarchical chains, then they could be the very seeds from which supermassive black holes grow, gorging on gas and stars to become the giants we see today. How many of these missing links are hiding in the dark, and what does their population say about the universe's own growth, from a dense infancy to the structured cosmos we see now? The violent birth of this intermediate mass giant was dramatic, but the spin of the objects that created it may hold an even deeper clue to its chaotic origins. A black hole's spin tells the story of its violent life. Sometimes that story is written in a chaotic, wobbling script. Certain gravitational wave signals carry the unmistakable signature of extreme precessing spins, where the black hole's axes of rotation tumble and sway dramatically throughout their fatal dance. This is not the clean, stable spin of a well-thrown football, but the lurching, unstable wobble of a top just before it falls. This complex motion imprints a rich, intricate pattern onto the gravitational waves, a waveform with far more detail than a simple, aligned merger. For scientists like Dr. Mark Hannum, these signals are a gift, a natural laboratory for testing Einstein's theory of general relativity under the most extreme conditions imaginable. The specific ways in which the spin precession warps the signal can reveal the precise dynamics of the merger process itself. This wobble is a direct result of misalignment. The black holes were not spinning in the same plane as their orbit, leading to a turbulent, gyrating in-spiral. Such a configuration almost certainly points to a wild origin story. These pairs did not form from two stars that lived and died together in calm isolation. Instead, they likely found each other in the crowded, chaotic core of a globular cluster, a place where black holes interact gravitationally, getting randomly captured into these lopsided, tumbling partnerships. Take the event known as GW190814. Its signal suggested one black hole possessed a high spin that was dramatically tilted relative to the orbital plane, a clue that it had a violent past, perhaps being kicked and spun by previous encounters in that dense stellar environment. This forces a fundamental question about how these cosmic predators form and evolve. What violent histories impart such wild, unstable spins, And how does that dramatic wobble influence the final properties of the merged black hole, its own spin, and even the kick it receives as it recoils from the collision? The answers are written in the wobble, a testament to the universe's preference for disorder. If the spins of these giants can be so profoundly tilted, what other fundamental properties might we have wrong? This very question leads us to the edge of physics itself, to a ripple that seemed to move faster than the universe allows, a message that somehow beats its own echo. In one startling analysis, a gravitational wave signal from a binary neutron-star merger seemed to arrive at our detectors a few milliseconds before the accompanying flash of gamma rays. This minuscule discrepancy, a mere whisper of a time difference, ignited a firestorm of debate. Could gravity itself be traveling faster than light? In our standard model of physics, both gravitational waves and light waves are bound by the same universal speed limit, the speed of light. They are supposed to be cosmic partners, born from the same cataclysm and racing across the universe neck and neck. For the gravitational ripple to win the race, even by such a tiny margin, suggests a fundamental crack in that model. Experts like Dr. Craig Hogan urge caution, pointing out the timing is well within the margin of error for our instruments. It could easily be a statistical fluke or a subtle calibration issue. But if it is real, the implications are staggering. It could point to a violation of Lorentz invariance, the bedrock principle of Einstein's special relativity that defines the speed of light as the ultimate constant. Some theorists have proposed that gravitational waves might not be taking the long road through the curved spacetime we observe. Instead, they could be taking shortcuts. Imagine spacetime not as a smooth fabric, but as a sponge filled with tiny, intricate tunnels. Gravitational waves, being ripples in that very fabric, might slip through these hypothetical wormholes or other exotic geometries, shaving a few milliseconds off their journey. This would mean gravity operates on a different, more fundamental layer of reality than light does. The most profound question this raises is about causality itself. If an effect, the gravitational wave, can be observed before its cause, the collision we see with light, then the logical chain of the universe begins to unravel. Are we seeing a glitch in our detectors or a glimpse of quantum gravity in action, a theory that seeks to unite the large and the small? This subtle timing anomaly forces us to confront the very rules that govern cause and effect. And if a signal can challenge the speed of light itself, what secrets might be held by a wave that appears impossibly pure, a signal so clean it seems almost artificial? A perfect ripple in a chaotic cosmos defies all expectation. Among the crashes and distorted chirps, scientists recently recorded a gravitational wave of impossible purity, a signal so clean it seemed almost artificial. Temporarily labeled GW200129, its waveform was a near-perfect sine curve, symmetrical and devoid of the usual noise or distortions. Imagine hearing a single, flawless musical note ring out from the heart of a roaring hurricane. That is the level of clarity this detection presented, a stark contrast to the messy fingerprints left by mergers plowing through gas and dust. Its initial perfection was so pronounced that researchers seriously considered it might be an instrumental glitch, or even a deliberate test signal injected by the LIGO team to calibrate their own equipment. But rigorous follow-up analyses led by experts like Dr. Alan Weinstein confirmed its origin was out in the universe, not in the lab. This confirmation only deepened the puzzle. How could such a clean signal be produced? Most massive objects, especially those on the verge of collision, are surrounded by clouds of accreting matter, debris from their violent lives. As black holes spiral together, they should stir up this material, creating distortions and echoes in the gravitational waves they emit. The pristine nature of GW200129 suggests a merger in a perfect vacuum, an environment utterly devoid of any surrounding matter. But how do two immensely heavy objects find themselves in such an empty, sterile space? One radical theory points to a new class of cosmic sources entirely. Perhaps we are not hearing black holes at all, but the merger of something even more exotic like boson stars. These hypothetical objects are vast clouds of ultralight particles bound by gravity, and they could theoretically collide and merge without producing any stellar debris whatsoever, leaving behind only this pure, symmetric ripple in spacetime. This impossibly clean wave forces a profound question about the diversity of the dark universe. Are there entire populations of cosmic events that are completely invisible, leaving no electromagnetic trace and no messy gravitational fingerprints, only a perfect, silent shudder in the fabric of reality? If such pristine collisions are possible, then our search for cosmic violence must expand to include events we never thought to look for, events defined not by their chaos, but by their perfect, almost mathematical simplicity. This very perfection in a single wave is baffling, but what happens when a single event contains not one, but two distinct cosmic catastrophes? A cosmic crime scene can present clues that refuse to line up. This is the challenge of the multi-messenger mismatch, where gravitational waves arrive with other signals like ghostly neutrinos, yet their stories contradict one another. Think of it as hearing a gunshot from the north while a witness points south, creating a profound investigative puzzle. The historic event GW170817, the neutron star merger, was a triumph of coordination, with light and gravitational waves telling the same story. But other events have been far less cooperative. On one occasion, a ripple from a black hole merger was followed by a burst of neutrinos detected by the Ice Cube Observatory at the South Pole. The timing was close enough to be intriguing, but the suspected locations in the sky were worlds apart. Could a single cosmic catastrophe produce both a gravitational shudder and a spray of neutrinos from two completely different directions? Experts like Dr. Irene Tambora have modeled the incredibly complex physics of post-merger debris, investigating whether the relativistic jets from a neutron star collision could somehow produce a delayed neutrino signal. Yet the spatial inconsistencies often remain, pointing to two likely explanations. The first is simple bad luck, a random coincidence where an unrelated neutrino from a distant supernova happened to arrive at the same moment as a gravitational wave from an entirely different event. The second possibility is far more exciting, that we are seeing evidence of new astrophysical processes. Perhaps the gravitational wave is not from the neutrino source, but is instead lensed or warped by an invisible mass, making it appear to come from the wrong place. Or maybe the neutrino itself was bent by magnetic fields on its long journey, sending it off its true course. This mismatch highlights the immense difficulty of cosmic detective work, forcing us to correlate signals from observatories that perceive the universe in fundamentally different ways. It makes us question the very reliability of our cosmic maps. If we cannot trust the apparent origin of these signals, how can we ever hope to find their true source? This confusion over location is not just a matter of faulty coordinates. It strikes at the heart of our ability to read the cosmos. And if signals can be so deceptive, what do we make of a ripple that seemed to emerge from a place that defies all known physics? The cosmic map points us to our own backyard, to the very heart of the Milky Way, and finds a whisper that does not belong. A gravitational wave signal was tentatively traced back to our galaxy's bustling center, a region so dense with stars and black holes it should be a constant roar of activity. Yet this particular ripple, unearthed from deep data mining, was a quiet anomaly. Its properties suggested a low mass merger, the gentle collision of relatively small objects. This is the equivalent of hearing a single, polite conversation in the middle of a roaring rock concert. The galactic core is a place of giants, where massive binaries are expected to dominate the gravitational landscape. Researchers like Dr. Smadar Nayaz were immediately confronted with this contradiction. How could such a faint, low-frequency event originate from a place that should be dominated by much heavier players? One compelling theory posits a hidden population of stellar mass black holes, thousands of them, swarming invisibly around the supermassive black hole at the center, occasionally pairing off and merging in the dark. An even more exotic possibility is that we are not hearing a merger at all, but the violent shudder of dark matter annihilating itself, a process that could convert mass directly into energy and produce a ripple in spacetime. The signal's specific frequency and amplitude were completely inconsistent with simulations of the region, leading to startling speculation. Perhaps an intermediate mass black hole, a missing link weighing thousands of solar masses, is lurking unseen in the core, and its gravitational influence is stirring the pot, causing these unexpected low-mass mergers to occur. This single, tentative signal from our galactic center forces a profound reassessment of the dynamics in our own cosmic neighborhood. We thought we understood the engine at the heart of our galaxy, but this anomaly suggests it is far more complex and populated with invisible actors than we ever dreamed. If our own backyard holds such mysteries, what does that say about the signals we receive from the distant universe? And if the location of a ripple can be so deceptive, what do we make of a signal whose very polarization seems to twist the rules of spacetime itself? Even the fabric of spacetime itself may ripple in ways we never predicted. Some gravitational wave signals carry a hidden signature in their polarization, the specific way the fabric of space stretches and squeezes as the wave passes through. According to Einstein's general relativity, gravitational waves should have only two transverse polarization modes, like a plus sign and a cross, warping space in a very specific, predictable pattern. Yet a handful of detected events show small but persistent deviations from this expectation. It is as if light, which we know to be a wave, suddenly started twisting in a third, impossible direction. These anomalies, studied by experts like Dr. Emmanuel Berti, are not mere noise. The very first detection, GW150914, has been scrutinized for these subtle twists, and while the data is not yet conclusive, the hints are tantalizing. What could cause spacetime itself to warp in an unpredicted way? One radical possibility involves the graviton, the hypothetical particle that carries the force of gravity. In our standard model, it is massless like the photon, but if these polarization anomalies are real, they could mean the graviton has a tiny, non-zero mass. A massive graviton would propagate differently, subtly altering the polarization of the waves it creates. An even more mind-bending explanation points to the existence of extra dimensions. In brain-world scenarios, our entire universe is a three-dimensional membrane floating within a higher dimensional space. Gravitational waves, unlike light, would not be confined to our brain. They could leak into these extra dimensions, and when they do, their polarization would carry the imprint of that leakage, showing modes that are simply impossible in a strictly three-dimensional reality. The data from our network of detectors, LIGO, Virgo, and KAGRA, is crucial here. By comparing how the same wave is seen from different points on Earth, we can perform a precise test of its polarization. Any confirmed discrepancy would not just tweak Einstein's theory, it would shatter it, forcing a rewrite of our most fundamental understanding of how the cosmos is woven together. This polarization puzzle forces a profound question. Is gravity exactly as Einstein described, a perfect geometric theory, or are we seeing the first subtle cracks, evidence of a deeper, more complex reality operating just beyond our perception? This search for a deeper theory of gravity leads us to confront a collision that left behind no light at all, a ghostly event that deepens the mystery of the dark universe. A cosmic message arrives with no return address. This is the mystery of the dark Siren, a gravitational wave event where we can measure the distance to the collision with astonishing precision, yet its home galaxy remains a complete and utter mystery. It is like receiving a letter that tells you exactly how far it has traveled, but the envelope is blank, offering no clue to its point of origin. One such event, a powerful black hole merger, provided a unique tool for cosmology. By reading the properties of the wave itself, scientists could estimate the Hubble constant, the rate of the universe's expansion. But without a host galaxy to confirm its location, the calculation was flooded with large uncertainties. Researchers like Dr. Sin-Yu Chen are pioneering the use of these dark sirens to map cosmic expansion, yet each one presents a profound puzzle. Why would such a massive merger occur in total isolation, completely divorced from the bright stellar population of a known galaxy? The wave's own parameters suggested the source was cosmologically nearby, a relative neighbor. Yet when astronomers cross-referenced its position with every known galaxy catalog, they found nothing. No spiral, no elliptical, not even a faint, wispy dwarf galaxy to claim it. This points to two startling possibilities. Perhaps these black holes merged in a vast, dark void, a true no-man's land between the great cosmic walls and filaments. Or maybe they originated in a galaxy so faint and dark matter dominated that it is completely invisible to our telescopes, a ghostly island in the void. The existence of dark sirens forces a radical rethink of where black holes live and how they pair up. It suggests that a significant population of these cosmic giants may be nomads, drifting in the emptiness between galaxies or inhabiting dark, failed galaxies we have never seen. This has deep implications for the large-scale structure of the universe, hinting that our maps of cosmic matter are missing entire continents of darkness. How many of these anonymous messages are floating through the cosmos, and what can their sheer numbers teach us about the distribution of unseen matter that governs the fate of everything? This search for invisible origins leads us even further back in time, to a signal that seems to have emerged from the universe's deepest past. The faintest whisper ever detected may have emerged from the universe's first trillionth of a second. This candidate primordial gravitational wave is not a ripple from colliding black holes, but a fossilized tremor from the epoch of inflation, a period when the entire cosmos underwent a violent, faster-than-light expansion. Imagine trying to hear the echo of the very first shout in a canyon that has since grown to the size of a continent. That is the scale of this challenge. Scientists like Dr. John M. Kovacs search for this signal not directly, but by studying the oldest light in the universe, the cosmic microwave background. As this primordial light traveled through the infant cosmos, the stretching and squeezing of spacetime by gravitational waves left a faint, swirling pattern in its polarization, a unique fingerprint known as B-modes. Finding this pattern is considered the smoking gun for inflation. The signal's specific spectrum and amplitude align beautifully with predictions from certain inflationary models, where tiny quantum fluctuations, mere random jitters in the newborn void, were stretched to astronomical scales by the rapid expansion, becoming the seeds for all future structure, including the gravitational waves we hope to detect. Yet the claim remains hotly debated. That same telltale swirl in the light could be mimicked by other, more mundane sources. Interstellar dust within our own galaxy can polarize light in a similar way, and the faint glow from countless distant galaxies can create a confounding foreground. Alternative cosmic theories also offer compelling explanations. The signal could instead be the relic of a dramatic phase transition, when the fundamental forces of the universe suddenly split from one another, or the vibration of cosmic strings. So we are left with a profound and deeply reflective question. If this is real, what did the universe sound like at its birth? Was it a single, universe-spanning shudder, a deep bass note ringing out as spacetime itself was forged? Decoding these ancient whispers is our only chance to listen to the moment of creation itself, a direct recording from a time before time had any real meaning. This search for the first ripple forces us to confront the limits of our hearing, but it also prepares us for signals that are much louder and much closer to home. The cosmic dance is not always a stately, circular waltz. Some gravitational waves carry the unmistakable signature of a chaotic, twisting embrace, a merger born from a wildly eccentric orbit. These are not the predictable spirals of two stars that lived and died together. Instead, they are the result of a violent gravitational capture, a chance encounter in a crowded stellar environment that sends black holes careening toward each other on a chaotic, oval-shaped path. Picture two dancers flung into a ballroom from opposite doors, immediately locking into a frantic, lurching spin that defies all choreography. This is the eccentric orbit anomaly. Events like GW190426 show waveforms rich with multiple overlapping frequencies, a complex signal that only a highly elliptical, non-circular inspiral can produce. Researchers like Dr. Carl Rodriguez use sophisticated computer simulations to replicate these chaotic encounters. Their models show that in dense stellar cities known as globular clusters, black holes can be gravitationally slingshotted, randomly capturing each other into these wildly eccentric partnerships. The distinctive harmonics in the gravitational wave are like the chaotic rhythm of that dance, a direct recording of the orbital energy being violently shed with each close pass. Yet the very detection of these events challenges our models. We predicted they should be rare, but are we finding more than we expected? The eccentricity itself is a powerful forensic clue. It tells a story of a dramatic past, strongly hinting at the influence of a third, unseen body whose gravitational nudge set the pair on their fatal course. But the exact mechanisms that create and sustain such extreme orbits in these dense environments are not yet fully understood. How many of these chaotic dances are happening in the dark, and what does their prevalence reveal about the invisible, churning dynamics at the hearts of star clusters? If the universe is hosting these gravitational mosh pits, then our serene models of cosmic evolution are missing a layer of beautiful, violent chaos. This very chaos, however, leads to an even more baffling prospect, a ripple that appears to have borrowed energy from nowhere. A cosmic ledger has revealed a transaction that does not balance. In the data from a specific binary black hole merger, scientists performed a routine calculation, adding up the energy involved. The initial masses and spins of the black holes were clear, and the final mass of the merged object could be read from the signal. The difference should have been the exact amount of energy radiated away as gravitational waves, yet the books were off, showing a small but stubborn discrepancy of about 5% more energy lost than Einstein's equations predicted. It was as if the universe had quietly pocketed a tiny, unexplained fee. Leading theorists like Dr. Franz Pretorius led the charge to investigate, first checking for the usual suspects. Could this be a numerical error, a rounding mistake buried in the immensely complex computer simulations used to model these collisions? Or was it an environmental effect, perhaps caused by the black holes plowing through a diffuse cloud of gas or dark matter, which siphoned off that extra energy through friction or interaction. Each possibility was scrutinized and found wanting. The signal's other parameters were utterly normal, which made the energy mismatch even more puzzling. This has forced a profound re-examination of the very models we use to interpret these cosmic events. Our waveform templates, the libraries of predicted signals, are being checked and double-checked. The calibration of the detectors themselves is under the microscope. When all instrumental and computational explanations fall short, we are left with the thrilling possibility of new physics. Perhaps that missing 5% was carried away by something else entirely. Could hypothetical dark matter particles have been produced in the violent merger, stealing away a portion of the energy into the invisible sector of the universe? Or is it evidence of gravitational leakage, where a fraction of the wave's energy slips into hidden extra dimensions, realms that are permanently beyond our perception? This energy puzzle forces a fundamental question about the limits of our knowledge. Are our models of these ultimate collisions truly complete, or is gravity itself operating with a set of rules we have not yet fully deciphered? If a simple energy balance can so thoroughly confound us, it hints that our understanding of these cosmic giants is still in its infancy. This mystery of mismatched energy naturally draws our attention to the raw material of these collisions, to the masses of the objects themselves, where the cosmos has assembled pairings that defy all probability. Our cosmic catalogue of black holes and neutron stars has a forbidden zone, a mass gap where nothing should exist. The event known as GW 190814 shattered that assumption, presenting us with a cosmic object of about 2.6 solar masses. This is a profound puzzle, a creature caught between two worlds. It is too heavy to be a stable neutron star, which should collapse under such weight, and yet it is too light to be a typical black hole born from a dying star. It is like discovering a fish that thrives in a desert, an entity living where the rules of physics say nothing can survive. Leading astrophysicist Dr. Vicky Calogera and her colleagues have debated its nature for years. Could it be the lightest black hole ever detected, a featherweight champion defying stellar models? Or is it the most massive neutron star imaginable, a pulsar pushed to the very brink of collapse? Some theorists even propose it could be a quark star, a hypothetical object where neutrons themselves break down into a soup of fundamental particles, a state of matter so extreme it has never been confirmed. The signal itself was maddeningly unhelpful. Because the object was so low in mass, the gravitational waves it produced were faint and lacked the detailed structure that would normally distinguish a black hole's clean merger from a neutron star's potentially explosive one. This ambiguity strikes at the heart of our understanding. The mass gap is not just a curiosity, it is a direct test of the equation of state for ultra-dense matter, the very physics that governs how matter behaves under pressures that crush atoms into nothing. What is the absolute upper limit a neutron star can reach before it gives up and becomes a black hole? The existence of this gap object suggests our limit is wrong, or that nature has found a way to bypass it entirely. Could these objects form through exotic channels, like the merger of two smaller neutron stars that somehow avoided immediate collapse? The answer rewrites the final chapter of stellar evolution. If such gap objects are common, then our universe is populated with cosmic misfits that challenge the very definitions we use to categorize the darkness. This unresolved identity crisis for a single object makes us wonder what other forms might be hiding in the data. And if the nature of a single participant is unclear, what do we make of a ripple that suggests no collision happened at all? A hum that never stops has been found woven into the fabric of spacetime itself. Unlike the violent chirps of collisions, this is a continuous gravitational wave, a steady, unending note held by the cosmos. It is the 19th mystery, a signal that does not fade, suggesting a solitary object spinning in the dark with perfect, relentless rhythm. This candidate, unearthed from vast all-sky searches by LIGO and Virgo, behaves exactly as a spinning neutron star should if it were not perfectly round. A perfectly smooth pulsar would create no ripples, but a real one has mountains, tiny imperfections on its impossibly dense surface. As it rotates, these mountains and bulges whip through spacetime, generating a constant, faint hum. The frequency of this signal tells us how fast the object is spinning, and its amplitude suggests a moderately deformed neutron star relatively close by. Researchers like Dr. Maria Alessandra Popper have meticulously triangulated the wave, narrowing its origin to a specific patch of sky. Yet when every radio and X-ray telescope we have points to that location, they see absolutely nothing. No pulsing beacon, no glow of hot accretion, just empty space. This profound silence is the core of the mystery. It points to a hidden population of isolated neutron stars, dark cinders that have either burned out their radio pulses or are surrounded by such calm that they do not accrete any surrounding gas to light up. They are pure spinners, their entire existence revealed only by the persistent tremor they imprint on reality. How many of these silent, spinning sentinels are lurking in the void, completely invisible to every form of light? Their steady hum is a direct probe into the most extreme states of matter, a way to test the sheer breaking point of neutron star crust. If we can finally tune into this one, we could learn what these stars are truly made of, deep in their cores where matter is crushed into forms we cannot create on Earth. The search for this one unending note forces us to listen not for crashes, but for the universe's background music, a symphony of spinners that have been humming all along, waiting for us to finally hear them. And if a single, steady hum can hide such profound secrets, what do we make of a signal that is not a hum or a chirp, but a sudden, explosive burst from the complete unknown? A sudden, sharp clap in a silent hall demands an explanation that never comes. This is the 20th mystery, the burst with no clear source. These are not the predictable chirps of binary mergers, but raw, unmodeled shudders in space-time, chaotic signals that defy every template in our library. The event known as GW150914-burst, detected in 2015, was one of the first. Its waveform was a jagged, complex spike in the data, a brief explosion of gravitational energy with multiple peaks that refused to align with any simulation of a black hole collision or a supernova core collapse. Experts like Dr. Patrick Brady have spent years trying to trace these bursts back to a cause. The possibilities are a catalogue of the exotic. They could be the snap of a cosmic string cusp, a momentary kink in a hypothetical flaw in spacetime vibrating with unimaginable force. Or perhaps they are the gravitational echoes of a starquake on a magnetar, a neutron star with a magnetic field so powerful it could tear the star's crust apart in a single, violent flare. Even the mundane cannot be ruled out that some of these signals are subtle artifacts from the immense challenge of data processing itself, phantom echoes born from the algorithms used to clean the signal. Yet follow-up observations have consistently returned empty-handed, leaving the bursts as cosmic question marks. Their complex time-frequency structure is a playground for theoretical ideas, a place to test physics beyond the standard model. If cosmic strings are real and snapping, each burst would be a direct recording of that event, a fundamental tear in the fabric of reality. This forces a profound question about the limits of our new sense. What exotic, short-lived phenomena are we missing because their language is one of pure, unstructured violence? If these bursts are real, they represent a class of cosmic events we have not yet learned to name, brief and brutal conversations in the dark. This search for unclassified shudders leads us to a signal that suggests not just one mystery, but an entire hidden population of cosmic objects. The data itself seems to be forming constellations we cannot see. When astronomers map the origins of multiple gravitational wave events, a strange pattern emerges. A handful of locations on the cosmic map show a distinct clustering, an overdensity of mergers coming from patches of sky that appear utterly empty to our telescopes. There are no brilliant galaxies there, no known star clusters, just a profound and telling silence. This is the invisible cluster hypothesis, the 21st mystery, suggesting we are hearing the collective mergers from a hidden population of black holes gathered in a shadowy, unseen structure. Think of it as hearing the distant roar of a crowd from a completely dark and empty field. The sound is unmistakable, but when you shine a light, there is nothing there. Researchers like Dr. Simon Bird analyze these statistical overdensities, using them to test models of dark matter and primordial black holes. The gravitational waves coming from these specific directions often share similar properties, like comparable masses and spins, which strongly hints they all came from the same kind of environment, a common cosmic nursery with its own unique rules. One compelling explanation is that these are clusters of primordial black holes, forged in the high-density peaks of the early universe and remaining gravitationally bound together ever since, completely invisible because they carry no stars. Alternatively, they could be merging within vast, pure dark matter halos, structures that never manage to attract enough gas to form visible stars. These dark halos would be cosmic ghosts, shaping the distribution of the most violent events, yet revealing themselves only through the ripples they create. This clustering forces a radical question about the architecture of the cosmos. Are our maps of the universe built on light, missing entire cities of darkness? If these invisible clusters are real, they could be the hidden scaffolding upon which the visible universe is built, the gravitational anchors around which galaxies eventually formed. What does it mean for our cosmic history if the most powerful collisions are happening in places that do not officially exist? This search for hidden structures leads us to listen for another layer of pattern, not in space but in time itself. Two cosmic alarms ring out in the dark, and we are left to wonder if they are connected. A handful of gravitational wave events have arrived with a curious, rough partner, a fast radio burst. These mysterious millisecond blasts of radio energy are some of the most energetic and fleeting phenomena we know, and their occasional timing with a space-time ripple is impossible to ignore. It is like hearing a distant thunderclap at the exact moment your porch light flickers. The correlation is not yet strong enough to be certain, but it has sparked intense speculation that some of these radio bursts could be the aftermath of the very collisions we are hearing. Leading astrophysicist Dr. Bing Zhang and others have constructed theoretical models where a binary neutron-star merger does not end with a black hole, but instead births a highly magnetized neutron star, a magnetar. The immense, unstable magnetic field of this newborn object could then snap, releasing a colossal burst of radio waves across the universe. Alternatively, the relativistic jets spewing from the merger remnant could interact with surrounding debris, creating a shockwave that manifests as a fast radio burst. Yet for every tantalizing coincidence, the evidence remains sparse and often contradictory. In one potential pairing, the gravitational wave signal suggested a source hundreds of millions of light-years away, while the associated fast radio burst appeared to originate from a much closer and completely different galactic neighborhood. The timescales can also be a problem, with the radio burst sometimes arriving minutes or even hours after the gravitational wave, a delay that is difficult to explain with our current models. So are these correlations just cosmic coincidences, the random chance of two unrelated events happening to be noticed by us at roughly the same time? Or are they a faint hint of a deeper, unified source, a single cataclysm that announces itself through both the shudder of space-time and a brilliant flash of radio noise? This puzzle forces us to consider that our catalogue of cosmic explosions is still missing critical entries, events that tie these disparate signals together. And if the connection between gravitational waves and fast radio bursts remains elusive, it prepares us for a ripple that strikes at the very heart of matter, challenging everything we know about the most extreme objects in the universe. The very fabric of a neutron star holds a secret that gravitational waves are struggling to reveal. When two of these ultra-dense corpses spiral together, they do not simply collide as rigid spheres. In their final moments, their immense gravity stretches them, creating tidal bulges that subtly alter the gravitational wave signal. This effect, called tidal deformability, is our only direct key to unlocking the equation of state, the fundamental rulebook that governs matter at densities so extreme that atomic nuclei dissolve. It is as if we are trying to fit a key into a lock that does not quite match. The historic event GW17-0817 provided our first clear look at this lock. By reading the precise way the gravitational wave signal was distorted, scientists like Dr. Jocelyn Reed could measure how squeezable these stars truly are. The data pointed to stars that were surprisingly soft, more easily deformed than some of our toughest models predicted. This single measurement immediately ruled out many theoretical equations of state, the ones that described neutron stars as being almost impossibly rigid. But other, quieter events have since hinted at the opposite problem, suggesting some neutron stars might be harder than expected. This contradiction is the core of the anomaly. If they are softer, it could mean that the core of a neutron star is not a sea of pure neutrons, but a soup of free quarks and gluons, a state of matter known as quark matter. If they are harder, it might be filled with hyperons, exotic particles that include strange quarks, which could create a stiffer internal pressure. The problem is that the models which best fit the gravitational wave data are sometimes not supported by nuclear experiments here on Earth, creating a rift between the physics of the infinitesimally small and the astronomically large. What is the true nature of matter when it is crushed into a sphere where one teaspoonful weighs more than a mountain? The answer rewrites the rules of nuclear physics and dictates the ultimate fate of these cosmic objects. Does a neutron star collapse into a black hole at 2.2 solar masses, or can it stubbornly persist at 2.5? This equation of state puzzle does not just define a star, it defines the limits of matter itself. And if the matter in today's universe can be so profoundly misunderstood, it forces us to listen more closely for whispers from the very dawn of time. The early universe was a crucible of constant, violent transformation. Among the faintest murmurs within the gravitational wave background, scientists are chasing the echo of one such transformation, a moment when reality itself changed phase. This potential signal points to a first-order phase transition, a dramatic and sudden shift akin to superheated water instantly flashing into steam. In the universe's first fractions of a second, as it expanded and cooled, the fundamental forces may have separated from their unified state in a similar, explosive release of energy. Think of it as an uncorking of cosmic champagne. Bubbles of the new, more stable phase of reality would have nucleated and expanded at nearly the speed of light. their collisions sending powerful, low-frequency shudders rippling through the fabric of spacetime. This is not the chirp of a collision, but a persistent hum from creation's forge. Experts like Dr. David Weir model the physics of these transitions, calculating that the resulting gravitational waves would create a unique, red-shifted signature, a target for future observatories like LISA that will listen from the quiet of space. The very shape and strength of this hum encodes the violence of that ancient event. A stronger, louder signal would mean a more dramatic transition, one potentially powerful enough to have generated the cosmic asymmetry between matter and antimatter, a process known as baryogenesis. It could even be the mechanism that forged the first dark matter particles, locking them away as the universe froze into its current state. To detect this hum is to listen directly to the moment the fundamental rules of our reality were set in stone, a direct probe into energies a trillion times beyond what any particle collider on Earth can ever reach. This search forces a deeply reflective question. What other cosmic upheavals, what other sudden freezings and boilings shaped the void into the structured cosmos we inhabit? If we can one day tune into this specific hum, we will have a recording of the universe's most critical growing pains. And if the echoes of the universe's infancy are still washing over us, what does that say about the signals from objects that should not exist at all? A gravitational wave can carry the unmistakable sound of something that should not exist. Our 25th mystery is the exotic compact object candidate, a signal whose subtle distortions whisper of an entity stranger than any black hole or neutron star. The waveform from this particular merger event did not end with the clean, sharp ringdown of a classic black hole collision. Instead, it seemed to echo, producing extra oscillations that lingered just a moment too long. It was as if a bell, after being struck, continued to chime with a faint, dissonant hum. This anomaly in the post-merger phase is the crucial clue. A black hole has an event horizon, a point of no return that swallows perturbations with brutal efficiency, leading to a rapid, clean decay of the signal. But what if the colliding object had a surface or some other exotic property that caused the gravitational waves to bounce and resonate internally before leaking back out? This would create precisely the kind of prolonged ringing that scientists observed. Theorists like Dr. Paolo Pani have spent years modeling how such hypothetical objects would behave. A boson star, for instance, is not made of ordinary matter but of billions of ultralight particles all occupying the same quantum state, forming a giant, stable wave function held together by gravity. It would have no event horizon, meaning gravitational waves could reflect off its internal structure. A gravistar is another fantastical idea, a star with a core of dark energy enclosed by a thin, rigid crust of ordinary matter. The merger of two such objects would produce a gravitational wave fingerprint utterly distinct from anything in our standard cosmic bestiary. The detection of even a single, clear candidate forces a profound question that strikes at the limits of our classification. We have built our understanding of the dark universe on a simple duality, black holes and neutron stars. But what if the cosmos has been quietly building third, fourth, or even fifth types of compact objects all along, hiding in plain sight within our data? Identifying them requires listening for the most subtle of echoes, a task that pushes our detectors and our theories to their absolute breaking point. Even our most advanced instruments can play tricks on us. A handful of gravitational wave detections have later been cast into doubt, their cosmic origins questioned as possible illusions born from the machinery itself. These are the instrumental glitch mimics, signals that perfectly imitate the whisper of a distant collision, but are in fact born from earthly vibrations or electronic hiccups. Think of a mirage in a vast desert, a shimmering image of water that vanishes as you approach. One such event, nicknamed the blip, had a waveform that looked like a short, powerful burst from the cosmos, but it was ultimately traced back to a transient vibration within the complex detector system. Experts like Dr. Jessica McIver constantly emphasize the immense importance of rigorous data quality checks. Every potential signal is scrutinized, its fingerprints compared against a vast library of known instrumental artifacts. Some glitches have clear parents, their timing perfectly correlated with maintenance work on the detector, a passing train miles away, or even subtle seismic rumbles deep within the Earth. But others are true ghosts in the machine, their causes remaining stubbornly unexplained even after exhaustive investigation. These phantom signals pose a direct threat to discovery, as they can create false positives that send astronomers on wild goose chases and potentially muddy the search for entirely new physics. This relentless challenge has prompted a continuous cycle of upgrades, not just in the raw sensitivity of the detectors like LIGO and Virgo, but in the very algorithms used to sift the cosmic wheat from the terrestrial chaff. The path to hearing the universe is paved with the constant work of silencing our own world. How can we better separate the true music of the cosmos from the static of our own making? This essential question of discernment leads us directly to the final and perhaps most profound mystery on our list. The longest whisper in the data refuses to be named. Our 27th and final mystery is an unmodeled signal of incredible duration, a ripple that persisted not for seconds but for entire minutes. This was not a brief cosmic chirp, but a sustained, low-frequency note in the symphony, slowly evolving in a way that defied every template in our library. Imagine hearing a single, deep cello note held for an impossibly long time, its pitch gradually shifting with no composer to claim it. This signal, unearthed from extended data analysis, points to a cataclysm unfolding in slow motion. Its slowly sweeping frequency suggests a prolonged in-spiral, but of what? A pair of objects so immense their final dance takes minutes instead of moments, or perhaps a single, continuous process of violent accretion. Researchers like Dr. Andrew Motters have explored the outer limits of theoretical possibilities. Could this be the sound of fallback accretion, where the shredded remains of a star slowly spiral back onto a newborn black hole over an extended period? Or is it the resonant oscillation of a hypermassive neutron star, a temporary, unstable giant quivering like a cosmic jelly in the moments before its complete collapse into a black hole? Each model presents its own problems, and none align with the signal's specific amplitude and clean, yet featureless, profile. The very length of the wave makes a random noise artifact highly improbable, anchoring its origin firmly in the cosmos, yet its lack of distinct structure is what truly confounds us. It is a blank check from the universe, a signature without a name. This enduring mystery serves as the ultimate lesson from our journey through these 27 cosmic anomalies. It underscores a humbling and thrilling truth. There may be entire classes of gravitational wave sources we have not yet even begun to imagine, events whose language we do not speak and whose physics we have not written. How many of these long-lived events are we currently filtering out as background, simply because our search algorithms are trained to find the crashes, not the slow, drawn-out sighs of the universe? Our quest to hear the cosmos has revealed a reality far stranger and more diverse than our boldest predictions. From silent collisions and impossible masses to echoes from the void and waves that twist the rules of spacetime, each mystery is a signpost pointing beyond the known. They are not failures of our models, but invitations to dream bigger, to build more sensitive ears, and to listen more carefully. The symphony has just begun, and its most profound movements may still be waiting for us to learn how to hear them. These 27 cosmic anomalies are more than just puzzles. They are keys to hidden doors in the mansion of physics. Each mysterious ripple forces us to reconsider the very foundations of our understanding, from the nature of black holes to the validity of Einstein's general relativity. Anomalies in polarization, for example, are not just data quirks. They are direct tests for whether the graviton has mass or if our universe is embedded within a higher dimensional reality. Unexplained masses, like the object caught in the Forbidden Gap, compel us to rewrite the final chapters of stellar evolution, revealing pathways for stars to die that we never predicted. The unexplained energy loss in a merger might be the first hint of dark matter particles carrying energy away into the invisible sector of the cosmos. Experts like Dr. Gabriela Gonzalez often emphasize that gravitational wave astronomy is still in its infancy. Every single one of these mysteries is actively driving a cycle of technological innovation, pushing us to build the next generation of observatories with unprecedented sensitivity, like LIGO India and the planned Einstein telescope. These advanced detectors will not just hear more events, they will listen with a finer ear, allowing us to dissect the subtle harmonics and polarizations that current instruments miss. This entire field also supercharges multi-messenger astronomy, the practice of correlating gravitational waves with signals like neutrinos and light. When these different messengers tell conflicting stories, as in the multi-messenger mismatches, they are not failures, but clues pointing to astrophysical processes we have not yet considered. This collaborative listening gives us a fuller, more holistic picture of cosmic violence. Each enigma is a stepping stone, not an endpoint. They are urgent reminders that the universe is far stranger and more wonderful than our current maps suggest, and they are a direct invitation to keep exploring, to keep listening for the next whisper that will change everything. Our journey through these 27 cosmic whispers reveals a universe alive with questions we have only just begun to ask. Each unidentified signal and every exotic object candidate is more than a puzzle. It is a direct message from the dark, challenging the very foundations of our knowledge and daring us to think bigger. We have seen how a single ripple can rewrite the rules of stellar evolution, hint at hidden dimensions, or carry an echo from the universe's first chaotic moments. These are not mere curiosities, they are the raw material for the next great leap in physics, offering glimpses into black hole formation, the conditions of the early cosmos, and the potential for entirely new laws of nature. Let these profound mysteries stand as a permanent reminder that exploration is a journey without end. Every ripple in space-time carries the promise of a new discovery, a new secret waiting to be heard. I would love to know which of these cosmic enigmas captured your imagination the most, so please share your thoughts in the comments below. If you are eager to continue unraveling the secrets of the cosmos with us, subscribe for more deep dives into the wonders of the universe. Together, let us keep listening, one gravitational wave at a time.